Good morning, everyone. Welcome to our week 4 of MATH13218 Advanced Applications of Mathematics. So far, we have been talking about ordinary differential equation, which is different from partial differential equation. And then we were mostly focusing on first order linear differential equation. So when we say first order, the power of the derivative is 1, right? Not the power, sorry, the order. Power is like a square or cube. But when we say the order is dy by dx or d2y by dx2 or the third order. So the order is 1. That is only y dash or dy by dx. That's what we have dealt. Now, so far we have the methods that we have seen are very specific. For example, equation that can be converted into variable separable or equation using Bernoulli's. So, like the P or Q type of equation, homogeneous, non-homogeneous. But there'll be many situations where none of this applies, right? Or it is very difficult to obtain the solution, like a lot of integration and complex integration. So as you can already observe that many of us are struggling, many of you are struggling to go through those steps, right? So even in real life, you end up getting a situation where you cannot integrate it, right? What will you do then? Then you have to come up with some technique where you can integrate it very easily, right? And numerical method is one of such beautiful technique. There are many numerical methods. Numerical methods. Part of numerical methods, some of them are finding approximation, some of them are for solving ODE, and many others. Okay. Here, we are very specific because of one lecture out of 9 sessions devoted to numerical method. So from our book, it is page 241, section 4.4.1. Right? So it's an entirely different chapter. And in that chapter as well, there are a couple of methods that I've mentioned, but we'll be focusing on Euler's and Euler's modified method, only two approach, right? Which is one of the easiest method you will find, right? So stay with me, hang on, and any doubt, we'll get in touch. FYI, I think last week I conducted an extra session. Recording is available on Moodle and on Teams folder as well, Teams group as well. Please revisit that. It was mostly to cater your needs of doubt because I got feedback. This is difficult you need. And some of you are struggling, to understand what's going on. So please, watch the recording. I'll try to repeat that, not in week 4, but in week 5. Yeah. So in week 5, I will conduct one more session and maybe depend on it then week after the midterm break, week 6, 7, 8, 9, whatever we need. I don't mind devoting an hour and a half, if that's beneficial to some of you. Okay, so let's get started in our journey. Right. So there is a lot that I'll have to read. What I will do is, give me one sec. I'm going to, read, sorry. I have something here which I want you to cover. Okay. So rather than what's on a slide, I really found something very interesting on another website. I hope this will make everyone can see that. What I will do is have the link pasted in the chat as well. Yeah, but that's the chat link. What I did, I just search for Euler's method, numerical method, Euler's method for solving ODE, and one of the few websites that comes up is this. I'll quickly take you to the beginning of it. So this is Euler's method. As you can see, it's a whole unit, right? As a whole unit based on numerical method. It is from Texas, one of the Trinity University. Trinity, and then up here you can go for the whole thing. I think I can go here, and here is the learning object, campus, bookshelf. I think there is a lot of topic that you can learn here. Recalculus and trigo, calculus. Let's say we go for differential equation. In differential equation, we got a lot of first course in differential equation for scientists and engineers. Second course, let's say we go with the first course. In there, we got first order linear OD, second order linear OD, numerical solution, right? So let's go for, we haven't gone for second OD, that's from week 5. So that's yet to come. But this is first order. So what is the free fall equation? What does first order? The application, right? If you are struggling with the application of the worded problem, you'll find a lot of them here. There's a good explanation, yeah. And then how you can do some extra reading, right? Where is differential equation applicable? How do we deal with it, And then, the variables and everything. Yeah. So if you go first order, what is first order? Then first order differential equation. In that, I think it will come the variable, separable, and the linear part that we have dealt with initially. Separable variable and separable equation. Some books have variable separable, some have separable equation, then linear first order equation. What is all this mu and q part? It's a different symbol. Yeah. So different material, different literature, different symbol, different explanation, but hopefully this will make sense to you. Yeah. Again, happy to put this. Let me go back to here. Again, go back. Yeah, first portion. And then I can again write in chat. Right, math.libretext.org, then bookshelves, differential equation, first course. Just even if you Google that, you will end up getting this. Okay. Third chapter is whole numerical solution. There we talk about Euler's method, Taylor's method, Runge-Kutta method, implementation of some numerical package and numerical application. Where are this applicable, right? Even when you refer to the book from Professor William, that has many of this covered, but this is an online version. Yeah, cool. So let me, I hope you are reading what, yes, you are reading what I'm sharing. Good. Right. So let me quickly go through the content, which is similar to what we will see in slides, but I just wanted to give a different flair. Yeah. So if an initial value problem, which many of the literature will refer as an IVP, initial value problem, which is y dash, because we are talking about first order linear ODE. So it should be given some initial value, right? Y of x0 is equal to y0. So whatever value inside is the value of x, right? And the final right-hand side is the value of y. Okay. This cannot be solved easily, right? It's necessary to resort numerical methods to obtain approximation of the solution. Now, hear this word. We are talking about approximations. the best approach is solve it analytically, right? You will have exact solution. But what if you cannot solve what is very complex, like I said? Then we should be closer to the solution rather saying, oh, I can't do it. But that's another approach. And then there is a modified or improvised Euler's method. There is that Runge-Kutta method. And then we have created, of course, Professor William has created the spreadsheet where you can compare various methods and see the error that you will obtain in each set. And error is like 0.01 or sometimes even lesser if you approach different methods. So what happens if your answer has to be 2.57? You'll get up some 0.01 type error. So 2.58 or something, but you'll get a still good feeling of what solution is or getting closer to the solution, right? So all the numerical method will be approximation to the actual solution. They are not the actual solution, right? Please bear in mind. Nothing badly today. Right. We are interested in computing approximate value of the solution of this set of equally spaced point, right? Along with this, I will explain this one, right? So Euler's method, an initial value problem within this interval, because you need some boundary where you will find the interval, is expressed by this y dash, which we know dy by dx is fxy, x0 to xn, y of x0 is y0, right? Right. Now, in order to obtain the solution, we will divide the whole interval into n equal parts, right? So let's say you got 3 points, A, the midpoint M, and B. How many parts you got? 2. So 3.2 part. Yeah, is it enough? When we talk about 3 points, right? First and second. 2 parts, you need 3 points. If you continue that way, 4 points, 3 part. 5 point, 4 parts. N plus 1 points, n part. So you got n plus 1 point, starting from 0 up to n. You got n plus 1 point. Now we will equally divide it in how many parts? N parts, right? So how it will look? They start from x0, go up to xn. You got x1 here, you got x2 here, x3. The last is xn, prior to that is xn minus 1, and in between some part. Now, they are equally spaced. If not, then there are different approaches available, and we don't deal Euler's method, but this all is edge. If you wanted to talk about the first part, sorry, the x1 point, that is the first x0 plus h. Then you keep adding h. x2 will be x0 plus 2h, or x1 plus h. x3 will be x0 plus 3, and similarly, xn will be x0 plus nh. So n equal parts of the whole interval x0 to xn. Right. It's represented in the I form, right? B is your xn, x0 is a in our method, and this is n. The gap, because if I say, yeah, from this, right? Every xi is x0 plus ih, okay? Now, there will be some error. I'll explain why there is an error, okay? If we denote the approximate solution, see, the word is approximate. The word is approximate, not the exact solution of this by this y0 to yn. What will happen? There'll be some error at each point. We call this error as E, which is the actual y of xi minus your approximate yi. Okay? And then we are talking about the error, that there are 2 types of error, the truncation error, round-off error, right? We'll talk about the truncation error here, round of errors when you're rounding, because the computation limitation, right? That's called a round of error. If you recall, when I was young, and maybe when you were kids, you had that normal pocket calculator, which is only 8 decimals. If I have to say go for 1/3, it will say 0.3 up to 7 digits, total 8 decimal on 8 digits only. It cannot be more than it is. And then I used to get that commercial calculator, which is 12 decimals. Yeah. Kira, are you able to hear me clearly or am I breaking up? Right. So here we'll talk about the simplest Euler's method. It's easy to explain, easy to understand, but it has a lot of error, right? And that is seldom used in practice because there are other better versions, better methods, right? Okay, and this is a whole explanation of what happens. I'll come back to this example, but until that, what I will do is stick to our PPT. Okay? I'll close everything that I don't need because I think my system is telling that that's learning low on resources. I don't know why. Okay. Right. So let's talk about, say, if you got an interval 1, 3. From that literature, the website is talk about A and B. Here we stick to one thing, that is x0 and xn, right? I wanted to divide into 10 equal parts because you need to be able to confidently determine your h. Okay. What is h? Or what is your xn? Will be x0 plus nh. So from that h will be xn minus x0 divided by n. Xn, which is 3, x0, which is 1, n, which is 10. So my h is 0.2. Okay. Now, please bear in mind, the smaller is your h, better is your, the less is your error, better is your answer, right? So even though up here it says h is 0.2, you will maybe go for 20 intervals and get h is equal to 0.1 or 0.05 or 0.25 or 0.01. Again, smaller is your h, better is your answer, less is your error. Right. So let's look at Euler's method and what it is and how it works and everything. Okay. H is the step size and usually fixed with the value of x0 minus xn by h the other way. Yeah. This is step size and usually fixed with the value of the gap, right? X0 minus xn over n. Using the first 2 point x0 and x1, we can then get the divided difference at x1, right? X0. Y dash is equal to. Now, I wanted to explain you everything. What is y dash, how it is, all that, right? So what I will do, I'll jump to the next part and keep coming back to this, okay? Right, so saying I want to explain why y dash is like this and what everything is, okay? Let's start. Okay. Let's say we are talking about solving a curve, right? That is solving the dy by dx part. Okay. So you got a curve here. Let's say this point is your x0, y0. By this time, I'm sure we all means what is the significance of this point. Y is the height and x is the distance. So this is x0 and this height here. We talk about tangent at this point. This height here, this bit, right? What we get from the horizontal line is my y0. Okay. Now, when we talk about tangent, the first thing that should come to our mind is so what is a gradient? Gradient, which from our basic y2 minus y1 over x2 minus x1, right? Now what I will do, I can also write this is y1 minus y0 over x1 minus x0, isn't it? Difference of 2 points. Okay. Now, this is the same as y1 minus y0 over h, right? What is this y2 minus y1? Change in the coordinates or the height. What is this x2 minus x1? The displacement, or how much the curve has shifted, the particle has moved and all that. Can we equally say that if this angle is theta, right, something is wrong. I think something is causing it to be slowed down. Give me 1 sec. Sorry, I think it will be faster now. It was just background syncing. Right. So it's y1 minus y0. Can we also, if I say this angle is theta, okay, so can we also say this point is being theta? And what is tan theta? Tan theta will be the, the gap, the difference in y, okay? If I redraw it again, I think it will make more sense if I draw it a bit differently. Right, it's another good. Fancy, isn't it? Right. Looks a bit tiny, but I'll still try that. That's a theta. If that point is my next point, this point will be what we call it x1. The point here is called x1, y1, right? And there will be this part. So this is what we call as delta y, the error part. This we call is delta y. Why do we call it delta y? Because of the tan theta part, right? What is tan theta here? Is the opposite over adjacent, right? So can we say your tan theta is delta y over h, because this part is h, yeah? Right? Therefore, delta y is h tan theta, right? Now, if you go back to the previous slide, what we are saying, y dash, right? Y dash, which is a dy by dx, is also change in y over change in x, or is the gradient, okay? So which is change in y over change in x. What is this h? It's nothing but x1 minus x0. So this is similar to your y dash as m as tan theta, right? Is y2 minus y1 over x2 minus x1, change in y over change in x, right? This is all the initial condition given to us, right? The differential equation and everything. So y dash, which is f of x0, y0, because that's a function of x given to us here, right? So if I leave my x as x0 here, then I'm talking about x0, y0, okay? F of x0. Now, what is y0? Y0 is the value of y at the point x0. Honestly, if you find this is difficult or find confusing, don't worry too much about it. Focus on a problem, solve, and that's it, right? Now, this bit here, y of x1 minus y of x0 over h, right? Which is your y dash. But what is your y dash? F of x0, y0, almost. So we say that, right? Or, and if you have to write it be simply y of x1, which is your first point from approximation, y1 minus y0 over h, we times it by h, therefore y1 minus y0 is equal to h, f of x0, y0, and from there You get y1 is equal to y0 plus h f of x0 y0. Okay. And this is what we are having here as well, right? So you got your delta y as h times tan theta, right? And what is your y1? Is your y0 plus delta y, right? Y0 plus h tan theta, and tan theta, as we now know, is nothing but the value of the function, right? So that is f of x0, y0, or y of x0, right? Okay. Now this is, some of them is already repeated. So from the Euler's method, what we now know, see, this is essential. Y1 is y0 plus h f of x0, y0. Now, if we had to go for y2, what you will do? Y1 plus h x1, y1. Y3 is y2 plus h f of x2, y2, right? And keep going. Then any I plus 1 will be I h f of xi, yi, where I is from 0 to n minus 1. The Euler's method, that is a forward step-by-step approximation process, right? We can also derive that the error in this Euler's method is order h squared, right? So if your h is 0.1, you'll approximately have an error of, 0.01, right? There is a detailed proof why order is order of h squared. And there is many theory how you can do this, and that's why there is a Euler improved Euler modified method, and there is this RK method and Runge-Kutta method. The link I shared in a chat, which I'm happy to post on Moodle as well, has a good explanation why order h square is the error. I'm not going for it now. Yeah. Right. So what happens? As we now know that Euler's method is an approximate solution giving method, right? So that uses a series of n tangent, first tangent, then second tangent, then third tangent. There'll be always some gap, as I explain it here, right? There's always some gap, and that gap is the error, right? This part here is the error. Okay. Right. At the n subinterval, the smaller is your interval, the minor is your gap, right? And minor is the error. Okay. Right. So let's now look at an example. Find the numerical solution to the following IVP, or initial value problem, of ordinary differential equation, ODE, using Euler's method with a step size of 0.1. So y dash is equal to y minus 2x over y of 0 is 1, y of x0 is equal to y0. So you are given this thing, h is 0.1. Okay, so what do we know now? H is 0.1. This is our h. Okay, what else we know? This is your fxy, isn't it? Right? This is your x0, this is your y0, right? If you just scroll through few slides back, yi plus 1 is yi h f of xi yi, right? So if I have to go for f of xi yi, that is this value, therefore yi plus 1 is equal to yi h. Wherever you find x, you'll replace h is 0.1. I can also write that. F of xi yi, that is yi minus 2xi divided by yi. Okay, this is what the same thing is. How many points we will go? 10, right? So 11 points, but 10 break, yeah, 10 steps. We will use computer software, in particular Excel is one of the easiest and easily available and easy to learn using the formulas in Excel. So we will use that to approximate it. We'll do one or two using, this thing, and then we will use Excel for computation. Okay, so it doesn't get that bad. Okay, right. So if your h is 0.1, we'll have to take n is equal to 10. So your I, as we say, 0 to 9. Okay. Let's start the first part. I is equal to 0. Okay. Therefore, your y1, value of 0, plus h, which is 0.1, y0 minus 2x0 over y0. Replace all the value that you know, right? What is the value of x0? x0 is 0 and y0 is 1. Replace it here. 1 plus 0.1, 1 minus 2 times 0 over 1. Yeah? Once you simplify, 1 plus 0.1, because this is 1, it is 1.1. Now, please observe every step. If you're not confident, check it. Because if your y1 is wrong, or some error in y1, your y2, hence y3, hence everything will be wrong. And the error will propagate. So it will really increase a lot, right? So please observe when you calculate your y1. Make sure it's error-free. Okay? Now we let I is equal to 1. What you will get? y2, y1, 0.1, y1 minus 2x1 over y1. Okay? We replace all the value y1, which is 1.1, 0.1, y1, which is 1.1, 2 times 0.1 over 1.1. Yeah. So that is 1.1 plus 0.1. 1.1, if you multiply it by 10, 2 over 1.1. Yeah. 2 over 1.1, I'll tell you exactly. 2 over 1.1, 20 over 11 should be 1 point. I'll tell you exactly because we need better answer. 1.1. Okay. So that is 2 times 0.1. Right. Sorry, I did something wrong. Give me 1 sec. 2 over 11, 0.1818. So that is 1.1 minus 0.1818. 1.08 times by 0.1 plus 1.1. That will be simplified to 1.1918. That's your y2. Okay. Imagine yourself doing it for 8 more steps. Right? You started with 0 and 1, easy. You got y1 as 1.1, your y2 as 1.1918, and then you keep on doing it. Right? Then you go for your, y2, y3 km, right? So let's try a few more, and then we will use the Excel. I'll tell you how to use the formula, and I'm sure it's not that big deal, but right. I is equal to 2. What will I get? My x2 will be 0.2, and my y2, I have to keep on going the same way, 1.19182. Yeah. So if you observe, the earlier was 1.19, 1.1918. Now it's 1.19182. Right? We keep going, and then we go for your y3. Yeah. What will happen to y3? Which is y2 plus h. Y2 minus 2x2 over y2 right? So y2 will be, once you plug in all the value, 1.1982, yeah, and everything, 1.19182 plus 0.1, 1.19182 minus 2x, 2x2 is 0.2, 1.19182, and simplify that. You will end up getting your y3 as 1.27744. That's your y3. Similarly, y4, y5, y6 up to y10. 4 up to 10. All right? This is how it. I etch this. You replace it here. It's just written a bit nicely. Yeah, 1.1982, or you could have written 1.19184 decimal, right? And this is a whole series of your approximations. So this is your x1, y1, x2, y2, x3, y3, x4, y4, x5, y5, yeah, 6, 7, all of that. Now, what is this yx? I'll explain that in a bit, yeah. Remember our method that we revised on Friday and learned last week about solution of ODE with the traditional method, what we learned, yeah? So that is using that bit, okay? So what is your y dash, or dy by dx is y minus 2x over y, okay? That Bernoulli's thing, yeah? If you rearrange it, y dash minus y is equal to minus 2xy power negative 1. Yeah. You got dy by dx, which is great, but the right-hand side has to be only function of x. This is 2x along with some y power. Doesn't matter, negative, positive, that's fine. So that only Bernoulli's method, right? So what is your capital P here? Is negative 1, right? What is your capital Q here? Which is negative 2x, right? And your n is minus 1, right? Remember z is 1 minus n. So 1 minus minus 1, therefore y square. So my z is y square. And then directly we go to direct part, dz by dx, yeah, plus 1 minus n, pxz is equal to 1 minus n qx, yeah. You plug all the value, I'll call it z dash, yeah. N is being minus 1, so this is like 2. Your px is minus 1, so can I say minus 2z, yeah, is equal to, this is 2 and this is 2, so that will be minus 4x, okay. Now we got a differential equation where z is our variable, right? And the small pq approach, yeah. This is your minus 2, is it? Since that's very simple, you don't have to go for small p and q, you can go directly. So your mu x, right, which is e raised to minus px dx, right, which is e raised to minus of minus 2 dx, and that will be e raised to 2x. This is your mu, right? Now the next step was the solution, z. My pen is acting funny somehow. Now I plug in it and I start working, even though it's 95% charge. I don't know why it's doing like that. Now it's working. How technology sometimes work out of mind. So Z, which is mu bracket C plus integration of, yeah, Q of X, yeah. You plug in everything, mu, which is e raised to 2x, c plus integration of q, which is negative 4x, mu, which is e raised to negative 2x dx. Now, as remember, last week you could split it out, this integration part, and put it back the value, or you can continue, right? So if someone had to continue your z, which is e raised to 2x, c plus, what will happen here? I'll just have a curly bracket just to separate it, right? This is your, I would not worry about -4, so I will keep it outside. Liate, L-I-A-T-E, right? From the liate. Now, by this time, I expect you have done enough practice of integration. If not, you will struggle all the time. L-I-A-T-E, logarithmic, inverse, trigo, algebraic, trigonometric, and exponential. Exponential comes last. So this is your V, and this is your U, right? Don't confuse mu and U. Okay. Right. So the formula says u integration v dx. So u integration of e raised to minus 2x dx minus du by dx, which is 1, integration of e raised to 2x, whatever that comes, dx, close all the bracket, minus 4 x e raised to minus 2x over minus 2. Yeah, the multiple of x goes in the denominator, minus e raised to minus 2x over minus 2. Yeah, and one more integration, dx. E raised to 2x, right? C minus 4 minus x over 2 e raised to minus 2x. This becomes plus half. There is another minus 2 going in denominator. So that will be minus x on 4 e raised to minus 2x. And then you multiply it inside, right? Remember, this is z. What is z? Z is y square. Yeah, z is y square. So you put back y is equal to plus or minus square root z, right? So whatever z you will get, you put it in there, and then you plug in the original value, which was 0 and 1. So you do it at every step. You did it every step, right? Now you don't have to really, I mean, you'll have to get rid of c because this is an initial value problem. So the value is given, but just complete it from here. Okay. Now, what I will do here is open the Excel and show you how it works on Excel. Right, so as I was saying, once you plug in the value and use the value, y of 0 as 1, you will finally end up getting y is equal to square root of 2x plus 1. You'll get plus or minus, but since your x is the positive part, you will have to keep the, the y is positive as well. So you got your y, okay? Now, let's go to the Excel part to actually compare everything in there, okay? So I got the Excel ready. Okay. Now what I've done here, please observe my formula. This is the I column, the XI column, YI, and YI original, okay? So I is 0 to 10. 0 is x0, y0, and the original is also 1. It's increasing by step 0.1. Now yi. What is yi? From our solution here, if you come to this, your yi is this, right? Yi plus 1, yi, h, yi minus 2xi over yi. Okay, So yi h, right? yi minus 2xi. Once you click here, you'll get up this thing. So I plus 1 is following the ith step in our Euler's method, right? And then division of xi, 2xi over yi, right? Once you have that, right, the next formula will mimic it if you just double click here, okay? Or use control D function. Use control D function for the same thing, right? Now, you will compare the error, okay? So what will happen? You need to go for the final step that I've done here. This thing, right? You'll plug in the value y of 0 is 1 into this one, which I've done pretty decent practice last week in week 3, the regular session, and the support session. Okay, so you'll end up that, and once you have your actual y value, square root of 2 times the same level, right? Because in the original, you are not going back. It's not a recursive thing. So square root of 2 x plus 1. If you talk about y1, square root of 2x1 plus 1. If you talk about y2, square root of 2x2 plus 1. y3 is square root of 2x3 plus 1. So that formula, again, double click and get it. And here you can compare the error between these two, right? Since your h is decent enough, you'll get some error, see 0.01. You're getting an error of 0.01. This is 7.8, this is 7.3, right? Okay. Right, so that's the Excel part of it. There is improved Euler. We are not going there yet. And then this is a comparison between the actual and the improved Euler. Which one is better and how that works. We'll come to that again, okay? Cool. Any question, please get in touch, okay? We keep continuing. We got one more problem. Given the initial value ordinary differential equation below, find this analytic solution. So the actual stuff that we were doing in the previous lecture. Find the numerical solution using Euler's method with a step size of 0.1 and access the absolute error. So don't worry about the plus minus part, absolute error, the difference between the two methods. You got your y dash or f of xy is equal to 2x squared minus 3x or 3 over xy between 1 to 2. x0, xn, step size of 0.1, so you'll have 10 iteration, and y of 1 is 1. So your x0 is 1 and your y1 is also 1. Okay. Right. The first thing is we will write them in the way we know it. So y dash plus 3x over y is equal to 2x squared. It is not Bernoulli, is a normal equation. dy by dx plus pxy is equal to q. So we start with the basic p and q approach. P is 3 over x. Qx is 2x squared. And then we go for the integration part, right? So what happens next? We go for mu. E raised to minus px dx, right? Because we are using integrating factor for the analytical solution, right? Which is, what is our p? E raised to minus 3 over x dx. E raised to, keep the minus outside. And this is ln x minus 3, or simply x minus 3, 1 over x3. This is my mu x. Having got my mu x, I'll talk about the solution y. Y is equal to mu x c plus integration qx over mu x dx. Right? So y will be mu x, which is 1 over x3, or x power minus 3 if you wanted to. However you write, doesn't matter. C, q, what was our q? Q was 2x squared. 2x squared times 1 over x3 dx, right? Sorry, my bad. right like this, so there is no confusion. Okay. So once you simplify your y, which is mu x1 over x3 c plus, you simplify it to x squared, and this will go up. Yeah, because it's denominator, so denominator will go to numerator, right? So 1 over x3 c. Don't worry about 2. This is x power 5. Integration is 6 over 6. And once you simplify it, c over x3, this is 1/3 x3. Yeah, this is your y. It's an initial value problem. The value is given. What was the value? Y of 1 was 1. So this is your x, this is your y. You put it back here. So 1 is equal to c over 1 plus 1/3. And then your c will be 2/3, which I put it back here. I'll get my y is equal to 2 over 3x3 plus x3 over 3. This is my y. You must get it correct. If that's wrong, then when you try to compare the error, it will be wrong as well. Okay. Now, so we got our y. You can write as fancy as you want. You can keep 1 over 3 outside, because when you are doing Excel calculation, you need to be sure. Plus x power 3. Yeah, just ensure that you are writing it correctly. Right. So this is your analytical approach, the first part. A, right? Now, find the numerical solution using Euler's method. That this is your yi plus 1 is equal to yi h f of x0, y0, right? So that's what we will do now, okay? This is our x0, y0, that's fine. Yi plus 1 to yi h. Write the formula in a few questions, so that's very clear in your mind. Xi, yi. This is my f of xy. Yeah. So yi plus 1 is equal to yi h is 0.1 2xi squared minus 3 over xi and yi. And then you keep changing your I. When your I is 0, you will get y1, which is y0 plus 0.1 times by 2x0 square 3 over x0 y0. You plug in the value of this is x0, this is y0. You plug in those values, so your y1 will be y0, which is 1, plus 0.1, 2 times 0.1 square minus, oh, sorry, not 0.1, 2 times 1 square. 3 over 1, and this is 1. So this is 2 minus 3 is minus 1, times 0.1, so it's minus 0.1, 1 minus 0.1. So y, so I'll just write it. Therefore, y1 is 0.9. Okay. Once I have my y1 hopefully correct, I can proceed to my y2. Just obtain a few, and then you can go for the Excel part. Okay, so I will have my x1 as 1.1. I already got my y1 as 0.9. Right, and now I will let my I is equal to 1. Okay, and so I will get my y2. Write it again. y1 plus h. It was 2x1 squared 3 over x1 y1. Yeah, and then put substitute all the values that we have seen. Y1, which is 0.9, 0.1, 2 times 1.1 square, 3 over 1.1 times by 0.9. And then you use your calculator for simplifying, and then add 0.9, that positive or negative, whatever. That will be 0.896545. That is your y2 when your x2, yeah, yeah, and then you keep going with your x2 and x3 and all that, right? Right. So here I have computed and kept everything in this table, which again, I'll bring it in Excel as well. So if x is 1.1, 0.1, and the actual, how do we go for the actual stuff? So this is the formula. You should write it in very easy form in Excel. So computation is error-free, right? And then the difference between them. Don't worry about the positive, negative. It's just the error, right? And that's why we call absolute error. So in Excel, we got a function called ABS. If you don't know something, just Google that, right? How to find an absolute value in Excel. Type that in Google or whatever search engine, and it should come up, right? Okay. Okay, so this is the Excel part of it. So it's all your I. X is just keep on adding 0.1 until you reach 2. Yi, which is this part. Sorry, this one. So if you go to slides like it was shown here, you need to write in a more simplified form. Yi plus 0.2 because 0.1 times 2, xi squared 0.3 yi over xi, right? So yi, and just however you write, as long as, just write everything there. Remember, in the Euler's part, you are referring to the previous thing. If you're talking about y1, it takes care of the x0, y0. Then y2, you're taking care of the previous y1, x1, right? And then your solution, which is this, y is equal to 1/3 of 2 over x3 plus x3. This is right how you write in the formula. And then, obtain everything. And then the difference, C, AB is absolute value function is used between the actual and the approximate solution, right? And that's all the error that you get. Okay. Hopefully by now it's starting making more sense. And the graph of exact solution and numerical solution through Excel. Okay. Okay. Now we talk about the next part of the session, which is improved Euler's method. So hang on tight. All right, now let's talk about our next method, which is improved Euler's method. As we have seen that there is a lot of error when we are approximating using Euler's method. So we go a step further and use the average of the xi and xi plus 1 and use that as the current step of yi plus 1. Let's see how that works. So to minimize the impact of such an error accumulated in Euler's method, we can use the result yi at xi from the Euler's method as a predictor for yi plus 1. So we are saying that yi plus 1 predictor is yi plus h f of xi by I. This predictor is then used to compute an auxiliary value to compensate yi plus 1. Okay. The new value called the corrected value or corrector is determined by yi plus 1, which is the yi, same thing, rather than using just this bit of h and this. What we do, we take average of it. So the xi yi term and the predictor value that we have taken, yi plus 1 predictor value, and average of it. And that's why you got h over 2 f of xi yi. And the second part is xi plus 1 yi plus 1 predictor method, right? Which is the average. So what this help is reducing the error that we are getting. Okay. So let's say this is your original thing. That's the curve that you are getting, right? We had our initial x0, we had our x1 here, right? And then when we are approximating, we are reducing the gap in here. Okay. Right. So yi plus 1 is yi half h f of xi by I, f of xi plus 1, yi plus 1, the predictor. This is two-step predictor corrector method, right? It's called improved Euler's method. Someone call it modified Euler method. In practice, we use the following form because it's very complex to observe it, right? So we use the following short notation using K1 and K2, right? So what is K1? We call this part as K1. We call this other part as K2, right? Now, please remember what is xi plus 1 is xi plus h. So rather than we wrote this, what is yi plus 1 predictor method? Yi plus 1 predictor is yi plus h ki f of xi by I. Yeah, here. This is also ki, if you call it, right? Okay, so that's been written here, right? And therefore, your yi plus 1 is half h k1 and k2, the average of k1 and k2. Again, this can be explained. This is like tan theta times h or delta y, right? Okay, let's look at the same example we have dealt, right? 4.16, which was the 2x over y minus 2x over y. Okay, the same step. Because then we can compare the Euler and improved Euler. What's the difference? How accurate that is, right? So what we do, we got our xi as x plus h. So our k1, if you again go back, k1 is f of xi by I, which is your question. This is nothing but xi yi, right? K2, what is K2? Is f of xi plus h, right? And y of yi plus h k1, xi plus h, right? So because this is, so, okay. If you wanted to go back, I can quickly take you 4.16 because that's a few slides early. So you can note down what exactly is f of x, y, this one, y minus 2x over y. Note it down if you have to. F of x, y. Okay, that's what we are using. So you got a k1 yi minus 2xi over yi. K2, what is K2? Again, come back here. K2 is the improved part, xi plus h, or your new thing, yi plus hki. So wherever you find your y, that is yi plus 1, right? This is the same thing. Y part, 2 times the x part, but x is xi plus h. Right? If you want, you could have written like yi plus 1 minus 2 xi plus 1 over yi plus 1, right? And what is yi plus 1 is yi plus hk1, right? What is xi plus 1 is xi plus h, and yi plus 1 is again yi plus hk1. And finally, your yi plus 1 is h over 2, the average of k1, k2, right? H times the average. Okay, don't forget the initial part. H is the same. We were given the condition y of 0 is 1. Okay, so we'll start with the first part. I is equal to 0. If I is 0, your first part is k1, which is y0 minus 2x0 over y0. Replace all the value. We remember y of 0 is 1. That means x is 0 and y is 1. 1 minus 2 times 0 over 1, that is 1. So I got my k1 as 1. Now k2, follow this formula, okay, which we got here, this thing. yi plus y0 plus kh times k1. Yeah, write it down before you plug in the value. 2 times x0 plus h divided by y0 plus hk1. Okay. This is your yi plus 1, 2xi plus 1, and yi plus 1. Because again in K2, You're still taking care of y over 2x over y, but your y and x is a bit different. Yeah. Right, now we plug in the value whatever we know. Y0, which was 1, h, which is 0.1, k1, it is 1, right? Minus x0, which is 0, h, which is 0.1, y0, which is 1, h is 0.1, and k is also 1. So 1 plus 1.1 divided by 2.2, sorry, 0.2 divided by 1.1. And that turns out to be 0.918182. That's your K2. And finally, your Y1, which is Y0 plus H over 2K1 plus K2. Once you plug in all the values, your this thing, Y1, plug in the values if you want. So that was, sorry, y0, which is 1, h, which is 0.1 over 2. This is 1 plus 0.918182. And the average will be y1, 1.551. This is the using improved Euler's value, right? It's written a bit nicely here. Yeah. So K1, yi minus 2xi over yy. K2, the yi plus 1 minus 2xi plus 1 over yi plus 1. And therefore this. When you let x is equal to 0, I is equal to 0, you get x0, y0. The same thing which we had done. Yeah, nothing. It was just written bit nicely, bit typed. Yeah. Okay. Once you get that bit sorted, then you go for the next one. Right? Take this is common. This keeps on carrying. Write it a few more times so you are very much familiar and comfortable with it, right? Your K1 will be now changed. Your K1 is, we still call it K1, K2, but for the next iteration, we don't call it 3, 4, and that, yeah? Y1 minus 2x1 over y1, plug in the value that you have obtained, and that's why we write it here. So you don't have to go back and refer to it. Y1, 1.0959, times x1, which is 0.1 there, but that simplify your K1 for the next iteration. Similarly, K2, please observe your steps. Make sure there is no mistake. And Y2 will be 1.1841. And similarly, we keep going, right? And therefore, you will improve your X1, Y1, Yx, the original value, which we already calculated, and the error. As you can see, error is already minimized, 0.0005 and all that, right? It's a lot smaller. And then a comparison of the Euler, which is like a rhombus shape, right? The actual and the improved Euler with a cross. As you can see, you hardly see any gap between the exact and the improved Euler. So just by taking the average of this, we are getting far better answers and less error. Okay, so this was our stuff. Sorry, example 1. Yes. It's the square root, the original one that we got here. Yeah. 0.95418322649 1.3416 and all that 4142 4832, just verifying. Yeah. Right. So that's correct. That's the original, this one, and this is an improved Euler for the same. So you got your K1, K2, and Yi, right? So that's using the improved Euler. So see, the Euler, it was 7848. Actual was 7321. Up here is actual 7378. So it's a lot closer, right? And then there is this chart which already been pasted there. Yeah. That's the same K1, K2, every calculation, everything. Yeah. Right. So that was all the comparison for the value. We go for one more example. The last one for the day, hopefully. Find the numerical solution to the following IVP initial value problem of the ODE using improved Euler method with a step size of 0.1. So dy by dx 1 minus x plus 4y, y of 0 is 1. Okay, I'm just not completing everything, but giving you hints for everything, something for you to take home question. So what we do here, first step is the analytical or exact solution, right? dy by dx is 1 minus x plus 4y. Convert that into linear form, which is very easy. This is all x form. This is x or constant. Very easy linear form. Finding out p and q, the mu method, integration minus px dx. Then the y is equal to mu c qx over mu x. Simplify, integrate where you can. Up here, this is separate, so this is fine, but this is the same LIATE approach, LIATE, because it's integration by parts. Your x will be algebraic, so it will come first, become u, and this is the integration of it. U integration v dx minus du by dx integration, and then simplified. This is with c, but you got a condition there. The condition is y of 0 is 1. Once you plug in, you will get the exact value of c. Plug in back. This is your y of x. You need that, right? You need it for comparing the exact Euler and Euler modified, improved Euler. For Euler, we have x0 is 0, y0 is 1, h is 0.1. Use this formula h and f of x I by I, which is your this part, 1 minus x plus 4y, 1 minus x plus 4y. Use the Excel thing or do few calculation and then use the Excel part. For improved Euler, you got x0 is 0, y0, h. K is f of x I by I, which is this bit. Yeah. K2 is, the same thing, but we use xi plus 1, right? The same thing, but we use xi plus 1, and here yi plus 1. Okay, and yi plus 1 is y0 h over 2. H is 0.1 over 2 is 0.05. K1 plus K2. Plug all the values in and calculate. Again, I got the Excel ready for you. It is this thing. Yes. Yeah. Y dash, y of 0, then you got y equal to 1 or 69. Yes, 4 is minus 3. Doesn't take long to calculate this, right? Really doesn't take long. Right. So what we did here, we got so y I have just written, then y and x and the ABS function, absolute of it. And then we got improved Euler here. So we got K1, K2, yi, y of x, which is still the same as this, right? And then the difference between them. Okay. And then I think it's been plotted as well. Yes, it's been plotted, which you will see in the slide as well. Plotting Euler, improved Euler, RK, and the exact. Don't worry about RK, it's Runge-Kutta. We haven't learned it. We won't learn it now. And that's the exact solution. Okay, thank you very much for your patience. I know it's a bit tricky content. I'm here to support, but you must practice hard. Every question once or twice until you get it. Right, I shared some website. I'll post those website link in Teams. Please get it from there and Moodle as well. Thank you very much. Thank you. See you next week.